Hello, friends. So we're back, and we're going to be starting chapter 11 now. So I like the way this is transitioning because we just did chapter 10, which was confidence intervals for means, and now we're going to talk about the hypothesis test for means. So a lot of things that we know about hypothesis testing is going to come back, but then we're going to kind of combine it with what we just learned about how to use inference for means. And apologies for my voice. I am what I think is battling COVID here at home. So let's see if I can get through this video. All right, so we're going to be carrying out significance tests for mu. I should have gone back to the targets here. So we're going to be stating the name of the test. We're going to check the conditions. We're going to be able to calculate standardized test statistics and find p-values so we can predict the population mean, or a test about the population mean, I guess. And then carry through the entirety of the significance test and be able to make a conclusion at the end of it to determine if we like what we see. And then also we're going to compare that to confidence intervals and how two-sided hypothesis testing does the same idea as a confidence interval, but it gives us a little more and frankly better information. So, carrying out a significance test for mu, we're going to be checking our conditions. So the same 3 conditions are typically checked each time. The random condition is stating that it comes from a random sample of the population of interest, or in the case of an experiment that we've done some assigning randomly. And then if you are sampling without replacement, we need to check the 10% condition. Again, that only applies when you're sampling without replacement. And then remember, we're not using large counts because these are means. We're going to use the quote large enough condition. So the central limit theorem essentially is what we're looking for. So the population would be, if the population is normal, then that means that we already know it's normal. But if we have a sample size that's larger than 30 or larger, then we can say it's approximately normal thanks to the central limit theorem. Now, today we're going to encounter something where maybe we don't know about the original population, and we have a small sample size. So then what do we do? Well, in that case, we need to kind of look at the data that we do have and determine whether we can assess normality that way. So in that case, we're just looking for like the absence of skewness and crazy outliers. And if that occurs, then we can go ahead and use T procedures. But if you do see strong skewness or outliers, then we cannot use T procedures for that. It is not enough to just make a graph on your calculator when you're assessing normality. You actually have to sketch the graph. So for most of us, a dot plot is the easiest graph we could possibly create. So that's what we're going to be working with in those cases. You don't have to do the dot plot if you've assessed normality in another way. So we have that battery example. I think we've come back to this one a few times now. And we have 15 AAA batteries from a simple random sample from the company. And we're going to first check the conditions. So the random condition has been met because it said they performed a simple random sample. And then it's only 15 batteries. I'm sure that's less than 10% of all the batteries that the company has. And then as far as the normality of it, well, our sample size is not big enough, and we don't know anything about the overall population of batteries. So we do have to look at the data plotted. So this is a cute little dot plot, and I'm not seeing any crazy skewness or outliers, so we can say that, it is approximately normal as far as the sample data goes. So we've met all 3 conditions. We're going to come back to that problem later on. So, as always, our standardized test statistic is found by taking whatever the statistic is from your sample, subtracting the parameter, and then dividing by the standard deviation of the statistic, which often we call the standard error. So ideally, in hypothesis testing, we would know everything we need to know. But unfortunately, we really don't know the mean and the standard deviation, right? Typically, of the entire population. So with that in mind, we can't use sigma. This is the problem. We can't use sigma. And we saw this kind of in the confidence intervals from chapter 10. So we're going to be using a t-distribution. So we're going to be finding a t-score or a t-statistic using x bar minus the hypothesized mean. And then instead of sigma, it's going to be the standard deviation of the sample divided by square root of n. And that's going to be our t-score, test statistic. Wow, it's going to be a tongue twister today. All right, so then, pause you for a minute, guys. Sorry about that. At all ages, guys, when your mom calls, you gotta You gotta talk to Mom. All right, I have to get out of this real quick. I think I lost my place. There we go. So I'm back. And we talked about how we're going to be calculating the standardized test statistic with our t distribution. So just like earlier, we talked about having what are called degrees of freedom. And we do have that t distribution, that table. And what we're going to learn in this chapter is oftentimes we're going to end up using technology for this degrees of freedom issue, especially when we get into two samples or paired samples. All right, so remember the degrees of freedom are found by taking your sample size and subtracting 1. This is a nice visual, I think, for what it means to use a t distribution. And we talked about the history a little bit back in chapter 10. And I did take the time to look up the history. And oh, see, the name already lost me. Hold on, let me go back and I took a screenshot of it. I think it's Gossett. I would hate to get this wrong. He's an important dude. All right, yeah, so William Gossett back in the early 1900s. He was working for Guinness. So I had that part right. So he was working for Guinness in Ireland, and he was trying to create some sort of a distribution because he was taking really small samples. And remember, Guinness, in my very blurry history story back in chapter 10, Guinness was really concerned about anything being published with their like secret formula and stuff. So um, he couldn't publish his findings for what he did here with this, what's now going to be known as the t distribution. So when he published this in the math community, he just signed it a student, a very vague student. Um, but his handwriting was awful, so no one could read his handwriting. So they just saw like a really large T and they started calling it the T distribution. Eventually, someone kind of translated his chicken scratch and said like, oh, it's the student's distribution. And that was kind of the affectionate name they'd give it, but a t distribution is what we call it. Now, the visual for this is depending on what your degrees of freedom are. Like here, this red line, that's the smaller degrees of freedom option of 2. You'll notice the tails kind of lift up, which gives you a lot of area under the tails. And then the more degrees of freedom you have, the closer and closer the tails come back down to looking pretty much normal. And if we kind of had a chance to work with the applet, you would see like, oh my gosh, look what happens when I get to like degrees of freedom around 30, which is our magic number for central limit theorem, right? So you would see that it really mimics the normal distribution at that point. And it's so close that it really doesn't matter. But for this chapter, we're going to stick with using a t distribution just so we kind of keep everything the same. And what else did I want to say about the t distribution? Oh, if you have a degrees of freedom where you're kind of out there, so like your tail has lifted up a lot because your degrees of freedom are like 3, 4, 5, don't be surprised if the t value that you're calculating is like a 3 or a 4. And we never saw that well, we did see that in the z scores, but when we saw it in a normal distribution for z score, a z score of 3 or 4 was like ridiculously far out with a tiny percentage in the tail. That's not going to be as true for a t distribution because that tail has lifted up, so there's more area. So don't panic when you're doing the calculations and you get a t score of like 3.4. Okay, it'll still work out. So, oh, see, I jumped the gun again. So they're similar to a normal distribution, having a mean of 0 and being symmetric, single-peaked, bell-shaped. But you're going to have more area in the tails on a t distribution, especially if your degrees of freedom are lower. All right, so as the degrees of freedom increase, it becomes more and more looking like the normal curve. See, I really got to stop and look at my next slide before I start talking. So we can use our friend table B to find the p-value from the appropriate t-distribution when performing a test about the population mean. In that better batteries example, the null hypothesis was that the true mean was 30, but the alternative was that those batteries actually lasted longer than 30 hours, so the alternative hypothesis is that it's greater than 30. And remember, there's a sample size of 15. So they took the data that they had, and frankly, for us, we would run one variable stats on those 15 sample data. They found the mean to be 33.93. They found the sample standard deviation to be 9.82. And then remember the hypothesized mean goes here and the square root of n goes down here. And they get a t-score of 1.55. Now, with a sample size of 15, they scale it back by 1 if possible to find the degrees of freedom. And then you would go visit table B. Now, if you look inside here, This is a little hard to look at, isn't it? Here's the row for 14 for degrees of freedom. And I'm trying to find 1.55 in the chart, which you're not going to find. So because it's in between here and here, that tells you that you're going to have an upper tail probability between 0.05 and 0.010. And you could make an estimate as to which one it's closer to, but we're going to end up using technology to find this more often than not, so don't panic. And they're saying, yeah, table B has limitations. Yeah, obviously. So there's a couple issues. It's only going to give you an interval for possible p-values, which is, okay, but it's not great. It's only going to give you the positive side of the test. Now, this particular batteries example, we did want the positive side of the tail, which they didn't draw it, but I kind of wish they had. But if you needed the negative side, you just would realize that there's twins, right? Symmetry. So whatever the positive side probability is, as is the negative. And then the degrees of freedom is not like it doesn't hit every integer, right? So it goes from 1 to 30, and then they start skipping by tens until they get to 100. Well, actually, no, not even tens. They skip by tens for a while, then 20s, and then they start skipping by like a lot. So remember on the degrees of freedom for table B, if you had like a true degrees of freedom of, I don't know, let's say like 90, well, that's a bad example. How about 92? Well, that's still a bad example, but anyways, it's not on the chart. You would have to go down to the lower degrees of freedom in the chart. So we would round that down to 80. It's just to be more cautious. That's why they're having you do it that way. But again, it's a limitation of the table. So with that in mind, we're probably going to use technology quite a bit. So where are we at now? We have a totally different problem with no context whatsoever, so that's helpful. We have a significance test, and the null hypothesis says that the mean is 5, and the alternative hypothesis says the mean is not 5. So we're going to have a two-tail here. And we're going to perform this at a significance level of 1%. So a random sample of size 37 from the population yields a sample mean of 4.81 and a standard deviation for the sample of 0.365. Again, no context whatsoever, but that's okay. We're just kind of going to do the first two steps. Explain why the sample result gives some evidence for the alternative hypothesis. Well, the alternative hypothesis is that the mean is not 5, and we just got a mean of 4.81, which, friends, that's not 5. So that's some evidence towards the alternative. And then for part B, calculate the t-value and then eventually the p-value. So remember, I love when you guys draw because it really gives me a visual for what you're thinking. This does not equal 5, so we're looking for a two-tail. So what we're going to have to do first, if you're hand calculating the t-statistic, is I'm sorry, the test statistic, you would use your sample mean of 4.81 minus the hypothesized mean of 5, divided by the standard deviation of the sample, which is also divided by the square root of n, 37, and you get a t-value of negative 3.16. Now, using the degrees of freedom of 36, at that point, you could go to table B, which is what they did, and they're going to tell you that, okay, well, it's in between these two, so the area on that upper tail is, yeah, something between here and here. So you can see they kind of just picked one of those. Actually, they did both of them. And then they doubled it because remember this is two-tail. So they're telling you that the true p-value, or sorry, I should say the p-value is between 0.002 and 0.005. So that is helpful because remember the significance level was 0.01, and anywhere in this interval of p-values that is less than 0.01. So in our next step, when we try to make a conclusion, we have enough information at this point to make a conclusion. Unfortunately, we have no context. I wish we had context. That might make that more meaningful. The other thing I would like to point out in this problem, I kind of wish as a class, maybe we'll do this, but we didn't go through all the other important stuff for significance testing. Like we didn't check any of the conditions. I know they already stated the hypotheses for us, but I think checking the conditions was important. Again, there's no context, so that's probably why they didn't bother, but something to point out. Sample size of 37 is bigger than 30, so yay. All right, so given the limitations of Table B, our advice is to use technology. Well, thank goodness somebody said it, to find the p-values when carrying out a significance test for a population mean. So on your calculator, remember how we have a normal CDF? There's also something called a T-CDF, which is the T-distribution, cumulative distribution frequency, I think is what that stands for. So your calculators, your newer ones, will prompt you. It's going to ask you for a lower bound and upper bound and then the degrees of freedom. You know what? I don't have my newer calculator pulled up. I feel like it prompts you for something else too, but we'll do that in class. We'll go through that quite a bit. Notice how they remembered it was a two-tailed test, right? So here, oh, you know what? I backed that up for a minute. What was that 1.55? That wasn't the t-score. What are you? What are you? Was that a totally different problem? I'm just like, yeah. Oh, that was the battery problem. Cute. Okay, so that was the battery problem. That wasn't even the same problem. How confusing. Now let's talk about that other weird problem with no context. So they went ahead and did the lower tail and then they doubled it to find the actual p-value. So this is the p-value, 0.003, which if I go backwards a little bit, it is in the interval that we originally calculated. So 0.003 is in between 0.002 and 0.005. Wow, that was a really long way of saying that. Now, also what I'm going to show you soon in technology is how to perform the entirety of the significance test on your calculator. It's pretty snazzy. Again, there are limitations to that because they do want you to understand the formulas and how things arrive. They want you to be able to do a problem that doesn't have any context. They want you to do a problem that's halfway solved already. So we're going to be flexible and we're going to be able to know that we can solve this problem multiple ways. All right, talking about solving problems, let's check our understanding. So the makers of Aspro brand aspirin want to be sure that their tablets contain the right amount of active ingredient. I'm not even going to pretend to pronounce that. So they inspect a random sample of 30 tablets from a batch in production. Now this is not an experiment, this is a sample, and it's a simple random sample, so mention that in your own little notes. When the production process is working properly, Aspro tablets contain an average of 320 milligrams of the active ingredient. The amount of the active ingredient in 30 tablets has a mean of 319 milligrams and a standard deviation of 3. So they've already found the statistics for your sample. That's very nice. And what they're going to want you to do first is state the appropriate hypotheses for a significance test. And there's a little bit of debate as we read through this question because some people might say, oh, they're worried that there's less than 320 milligrams of the active ingredient. But I don't think they really care if it's less than or greater than. They're just concerned that the average amount is different than what it's supposed to be. Because if you have too little of an active ingredient, that's a problem. And if you have too much, that's a problem. So what you're going to find as I sneak a peek at the answers is the hypothesis are that the mean is equal to 320 milligrams, and the alternative is that it's not equal to 320 milligrams, where mu is the true mean amount of the active ingredient measured in milligrams in Aspro tablets from this batch of production using a significance level of 5%. Now, they didn't tell us the significance level of 5%, so we always assume 5% when they don't tell us. All right, now we're going to check the conditions to make sure that we can carry out this test. So random, yeah, because simple random sample. Cool, cool. 10%, I'm positive that they make more than 300 tablets, so 30 is less than 10% of all the tablets made at on this particular batch. And then the large enough for the large, I shouldn't say large counts condition because it's not proportion, but the central limit theorem essentially, 30 is greater than or equal to 30. So all three conditions have been checked. All conditions are met. All right, so now they're going to want us to calculate the standardized test statistic. So let's go through this the long way using the formula because it is important, and then we're going to find the p-value, and for goodness sake, please draw out the curve. So calculating the test statistic, we're going to use our formula that starts with the sample mean, which was 319, minus the hypothesized mean, which is 320, divided by the sample deviation, which is 3, which is also divided by the square root of n, which is square root of 30. So that's what we see right here. So that's them calculating the standardized test statistic. And this is what we used to call a z-score, but today we're calling it a t-score. So remember our hypotheses was that it was different. So on your curve, you're going to mark negative 1.83 t distributions, but you're going to have to mark it in the positive direction as well. So we're looking for the area in both these curves together. So this is a t distribution, and notice the label of this, the title of it. It's a t distribution with degrees of freedom of 35. So that is coming from, um, hmm, I feel like there's a typo somewhere here. Maybe not. 36 minus 1. Where's that coming from? Y'all, I think that's a typo. I don't know what happened here. Okay, well, when I teach this problem live, I'm going to have to change something here because n was not 36. So I either have to change this to a 36, which changes everything, or I have to just change the whole problem. Either way, the real degrees of freedom on this problem should have been 30 minus 1, which is 29, which is available on the table. But like we're going to learn in a moment, none of us are going to start using that table. We're going to keep using technology one way or another. So, um, man, they really skimped here. I feel like I took a picture of something wrong. I'm going to have to redo this problem, I think. All right, here's what I'm going to tell you guys. If we use technology and we use the t-score of negative 1.83 and we find the area from there down using t distributions, t-CDF, you're going to find an area and then you just need to double it. And then right now, you know what? Let me go ahead and do that real quick on my calculator. Hang with me. Let's see how far off we are. I feel like I botched this problem, not just with answer key problems, but something terrible. All right, so I'm going to the distribution menu. I know you can't see my calculator, but I'm going there. And then I'm going to choose number 6 on my calculator, says TCDF. My lower bound, something ridiculously stupidly negative. Negative 999 is my go-to. My upper bound is negative 1.83. Degrees of freedom, I'm going to go with the actual information, which we have. So I'm going to put 29. And I'm pasting it in. And I'm getting a 0.03877, yada yada, but I'm going to multiply it by 2 because we have two tails. And I'm getting a p-value of 0.0775. So that's a p-value of 0.077-ish, which is obviously greater than my significance level, which is, yes, that is the right answer. Okay, so something happened here. This is just them using table B and being weird about it with the wrong problem, I think. So this part 4 is correct. That is the p-value I got using technology. But anyways, the point is, if your p is greater than your alpha, you fail to reject the null hypothesis. We do not have convincing evidence that the true mean of the active ingredient is different than, in this batch, is different than the expected mean of 320 milligrams. Wow, sorry. Botch, botch, botch. So the 4-step process, guys, it's the same. We just have to kind of realize the devil is in the details. So state the hypotheses, null and alternative. Make sure you state the significance level and define the parameters for what they really, really are. And then at that point, you're going to identify the inference method and check the conditions. So for us, and I'll show you in a minute what we're going to call this, but we have names that come from our calculator, and then we have names that it's really called, like in real life. So we have to make sure that we understand what's the calculator speak for it and what are we really doing. Check our 3 conditions if applicable, depending on what the situation is. Actually do it. You need to calculate the sample statistics, so the sample mean and standard deviation if they're not already given to you. You have to calculate the t-statistic, and then using some method, you got to find the p-value. And again, I'm going to show you how to do all that on the calculator in the do step, but you have to be very careful how you indicate to your reader how you're getting this information. You have to label everything really nicely too. And then make a conclusion, and you're going to have to do the 2-step process for the conclusion. So compare the p-value to alpha, and then say whether you reject or fail to reject the null hypothesis. And then based on that, you say we either do or do not have convincing evidence, yada, yada, yada. All right, let's talk more about these conditions. So let's break down this formula like we always do. So that first condition about it being random, that's what allows you to estimate that your sample data is a good estimator for the true mean. And if you don't sample it properly, then you've created bias in your sampling method, then it's just not a good estimator. So That's bad. Um, Also, maybe a little star in your notes here, the random condition can also be applied to random assignment if this was an experiment. We saw that before in the proportions chapter. All right, the 10%, oh, we're going to skip that. The normal or large enough sample condition is what allows you to use the t-distribution. So you're going to use a t-distribution with n minus 1 degrees of freedom, assuming that your sample size is either large enough, so 30 or bigger, or possibly your original data was normally, or sorry, your original population was normally distributed, that works. Or if none of those apply, then you can draw me a little diagram, a little distribution of your sample data, and as long as you don't have some obvious skew and outliers, then you're good to go. Now the 10% condition, and this is only something you have to worry about if you're sampling without replacement. So to use this little baby formula, as long as you're sampling without replacement, in a case where you actually are sampling that way, you have to check the 10% condition. That's the same 10% condition we've been checking for chapters now. And that's, again, assuming you're sampling from without replacement from a finite population. So we're going to see a problem coming up in this chapter where it's like you're testing river water. Like there is no finiteness to that, right? The water's just going to keep replacing, so you don't have to worry about that. All right, here's a nice diagram of what our hypotheses would look like if we drew them on a t distribution this time. I think that's always helpful to look at. Nothing new there. Oh, speak of the devil, river water. So a level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. The researcher measures the DO level at 15 randomly chosen locations along the stream. Here's the results. So a couple questions here. An average dissolved oxygen level below 5 milligrams per liter puts the aquatic life at risk. So did the data provide convincing evidence at the 5% significance level that aquatic life in the stream is at risk? Well, that's a very loaded question because that asks us to perform a significance test, so that's going to take us a minute. And then we're going to use our conclusion to determine if we made, oh, there's our friends, type 1 and type 2 error possibly could have been made, and then talk about what that looks like. So still the 4-step process, and we're going to start with state. So we are going to test the null hypothesis that the DO level is 5 milligrams per liter, and the alternative hypothesis is that it is less than 5. And now we need to state what our parameter mu stands for. That is the true mean dissolved oxygen level in the stream. I kind of wish they put labels on that, but whatever, milligrams per liter, using significance level of 0.05. I think, to me, labels are important just because labels are important, right? So you either have to, most people put that right here in the parameter description, like dissolved oxygen level measured in milligrams per liter. All right, anywho, there's the state step. Now we are the planning step. So this is not working, hold on. The official name, there we go, the official name of what we're doing here. This is called a one sample t-test for mu. So one sample, because we are taking one set of sample data, we're performing a t-test, not a z, but a t-test, and we're trying to test this against mu, the mean. So checking our conditions, random, yes, they did some randomly chosen locations. That was good, good. They don't have to check the 10% condition though, because like I talked about, there's an infinite amount of river water. Like you're not replacing, it doesn't matter if you're replacing it because it's river water, right? It's replacing itself. Go nature. All right, now let's talk about the fact that we didn't do enough samples to satisfy the large counts, I did it, central limit theorem. And it also didn't tell us that the original population of oxygen level was normally distributed, so we have to take our data and actually graph it. They chose a histogram, which probably makes more sense with the way the data is looking because the dot plot on that would look atrocious. So they've made some buckets with some obvious integer values. And that looks pretty good, right? It's roughly symmetric, no crazy skewness, no outliers. So we're going to go ahead and say that we can use we can say this is approximately normal and move on to the do step. So right now we're still doing this all by hand, and that's okay. So how they found the x bar and s sub x is they took this data and they entered it all into list 1 in their calculator. Okay, so we went stat, edit, and entered this into list 1 or some list of the calculator. And then they performed one variable stat. That's where you go back to stat and then calc, and then choose one variable stat using list 1 as your input. And then it's going to spit out a whole bunch of statistics to you, but the two you're interested in are the sample mean and the sample standard deviation. So you're going to need to copy that down. You do not have to tell your reader or your teacher where you got these from. I guess if you did, you just like a little extra, and I like that. So now we're going to calculate our test statistic. So that sample mean you just found minus the parameter that we're testing against, which is 5, divided by that standard deviation you just found for the sample, divided by the square root of n. And this is our test statistic of negative 0.94. All right, apologies, my recorder cut me off just then. All right, I think we were talking about calculating this test statistic here. So the mean that we just calculated from the sample and the standard deviation goes into the formula down here. This 5 is from the hypothesis. And then we're dividing by the square root of n for that standard error. And we're getting a t-score of negative 0.94. So remember, the alternative hypothesis was that it was less than the value. So we're looking for a lower tail here. And this is a t-distribution with degrees of freedom of 14. So make sure if you're drawing it, you're labeling it with that. So as far as how you find that area for the p-value, you could use the table and find out that the answer is between 0.15 and 0.2 for p-value. Or you can use technology, and in a minute I'll show you how to use technology for the whole shebang. But either way, you get about 18, 20% for a p-value. And when you compare that to the 5% significance level, that tells you something. So because our p-value is greater than our significance level, we fail to reject the null hypothesis. We do not have convincing evidence that the true mean of the dissolved oxygen level in the stream is less than 5 milligrams per liter. So now they're going to talk to you about errors, and we need to think about what kind of error we possibly just made. So if we fail to reject the null hypothesis, that means we run the risk of making what's called a type 2 error. That's where you fail to reject the null hypothesis, but turns out the alternative actually is true in real life. So in real life, in the context of this problem, that means that the true mean dissolved oxygen level is less than 5 milligrams per liter. But because of our sampling, we didn't find significant evidence in our test to imply that. So all the aquatic life could be at risk, and we don't know it. So if that's a concern of ours, then we got to think about how we can lower the risk of a type 2 error. And remember, we have a couple ways of fiddling with that. So I kept promising you the calculator. There's a way to do this on the calculator, and there is. It's called a t-test, and it's in the stat test menu. So I'll show you in a minute what you do and what you press, but for this particular example, they're using a mean of 5, and this is the river example. So we went to stat test and then chose t-test. Now it's going to give you an option. Do you have data or do you have stats? So remember, when we calculated this by hand, we had to put all of our data into list 1 and then find the sample mean and standard deviation. Well, this is kind of going to be a one-stop shop. It's going to do it all for you. So if you went ahead and put your data into list 1, you're going to tell your calculator that down here. And then if you already had the stats, you could just type them in freehand. But we do have our null hypothesis as being equal to 5. Data's in list 1. Frequency list, remember, just means that you're not multiplying all those values by anything, so just leave that as a 1. Our alternative hypothesis was that it was less than 5. And then you have a choice to calculate or draw. Now, calculate gives you a lot more information than the drawing. I tend to do both when I'm nervous on a test. So I will use the calculate option because that's going to kind of give me everything. But truly, the only things you need are the t-statistic and the p-value. So I will say, no, I take that back. You do need the x-bar and the standard deviation. So if you've already calculated that, good on you, but your calculator will do it for you right here. You also would need to mention, if you're using your calculator, that A, you used your calculator t-test, and also that the degrees of freedom are equal to 15. So that is nowhere on your calculator. You have to be able to remember that. Yeah, and that's that. They're like, go ahead and use your calculator if you want to on the do step. Just a couple of words of caution. You got to make sure you state what you're doing. Make sure you give it the proper name. It's a one sample t-test from you. Report the t-value and the degrees of freedom and the p-value. Get them all down and you'll get credit for the do step. Now, remember, if you do anything wrong, and because you're not showing work, you run the risk of getting an incorrect on that entire section, even if it's like mostly right. All right, so this is a check your understanding problem. We have a teacher who suspects that their students at their school are getting less than the recommended amount of sleep, which is 8 hours a night on average. So to test that belief, they took a random sample of 28 students and asked how much sleep did you get? So here's our data. This is why we're using t-test for means, because this is going to be an averaging kind of a problem. We have quantitative data. So do these data provide convincing evidence at the 5% significance level to support the suspicion? Well, that's a very loaded question. They want you to perform an entire significance test. So I'm going to show you the answer. Pause the video in a moment. Try this one on your own. Here we go. So the null hypothesis is that the mean is equal to 8, and the alternative is that it's less than 8. And mu is the true mean amount of sleep measured in hours that the students at this school will get each night using a significance level of 5%. That's the test that we're performing. The official name of that test is a one sample t-test for mu, and it is random because they selected the people randomly from the sample for the sample. They are sampling, so we need to check the 10% condition. I'm sure 28 is less than 10% of the population of all the students. And then we don't have enough of a sample to claim central limit theorem. You need at least 30. And we don't have anything about the population. So what we have to do is take our sample data and draw a distribution of the sample data. And here it is as a histogram. And I do notice that there's no outliers and it's pretty symmetric, not skewed in any way. So we're going to go ahead and move on and use the T procedure. Speaking of which, it's the do step. So if you're using your calculator flat out, you still need to indicate your x bar, your s sub x, your t, your p-value, which is down here somewhere, and then that you have a degrees of freedom of 27. So they used a couple different methods here. This is the old school calculation. Now they found this x bar and s sub x by using list one, using one variable stat. Remember that's in the stat menu. But remember, your calculator will also give them to you if you're using the t-test. If you're an old-fashioned table beer, you're going to find the p-value is between 0.0005 and 0.001. If you're using the TCDF to find this little tiny area down here, you're going to find it's pretty tiny, 0.0006. And if you use the t-test, you're going to get something really small like this guy. It's actually, I think, equivalent to that. So because our p-value is less than our alpha, we reject the null hypothesis. There is convincing evidence that the students at this university get less than the recommended 8 hours of sleep on average. Sleep more, kids. It's important. All right, so now to talk about two-sided tests and confidence intervals and how they go hand in hand. So we kind of talked about this back in chapter 9, I think, with the proportions, but now we're going to talk about the means. So there's a link between two-sided tests and confidence intervals for a population mean, and you can actually make a conclusion for inference based on the confidence interval. So if you have 95% confidence interval for mu and it does not capture the null hypothesis, so in that little interval you're given, if the null hypothesis is not in there, you have enough evidence to reject the null hypothesis right there. If you are performing a two-sided test, this only works for two-sided tests, and then this particular one would have to be at the 5% significance level because of the 95 complement. On the contrary, if you're performing a 95% confidence interval and it does capture that null hypothesis, then you should fail to reject the null hypothesis. So yeah, you should fail to reject the null hypothesis because it was within those plausible values, which means it's okay. Or at the very least, I should say, I don't have evidence to reject it. And again, that's specifically at the 5% significance level, only if you're performing a two-sided test. So this only applies for two-sided tests. And it would be true for, a 99% confidence interval at the 1% level, a 90% confidence interval at the 10% level. So all of those would work for making conclusions on your inference. Oh, the pineapples are back. If you remember, this was a pineapple question about, hey, we changed our irrigation system. And they want to know if it had an impact and changed the size of the pineapples or the weight of the pineapples. So typically the mean of the pineapples, if I remember from the other problem, was 31 pounds. That doesn't sound right. 31 pounds is a huge pineapple. 31 ounces? I don't know. 31 something. I remember the number 31. So the hypothesis test was that they were different, if you remember. Not that they were greater or lesser, just that it was, oh yeah, there we are, different. Where mean ounces, that makes more sense. Mu is the true mean weight in ounces of all pineapples grown in the field this year. So the null hypothesis is that it's still 31, and the alternative is that it's just something different. So we have a two-sided test, and then we're checking our conditions. The random sampling of the pineapples, check, 10%. I don't know much about pineapple farming, but I'm going to assume 50 is less than 10% of all the pineapples in the large field. And then we have a large enough sample. Thanks to central limit theorem, 50 is greater than or equal to 30, so check. Part C says, here's a 95% confidence interval. I think we actually had this problem back in chapter 8 when we did confidence intervals. And they talk about the mean weight of the pineapples this year being between 31.255 and 32.616. So because that confidence interval does not include 31 as a plausible value, it would be right before the confidence interval, that's enough evidence to say we can reject the null hypothesis at the 5% level. We do have convincing evidence that the true mean weight of all pineapples grown this year is not 31 ounces. Again, that's only at the 5% level, which they did state here in the problem. And then part D, can we conclude that the different irrigation system caused a change in the mean weight of the pineapples? Explain your answer. And this is unfortunately a no. This was not a comparative experiment. So there's a lot of things that could have affected the mean weight of pineapples this year, and it might not have had anything to do with the irrigation system. It could have been the weather, could have just been the soil was weird, bad farming techniques, could have been all sorts of things. Again, I don't even pretend to know how to farm a pineapple farm. So unfortunately, because we basically just did a study of sorts, this was not a comparative experiment, so we can't make that conclusion. All right, I love this part. Using them wisely and practical importance. Statistical significance is not the same thing as practical importance. So to evaluate practical importance, give a confidence interval for the parameter in which you are interested. That's good advice. Confidence intervals are not used as often as they should be. Like people kind of like the hypothesis testing. I don't know why. I think it's just something we hear in everyday language and we're like, yeah, that makes sense. Well, confidence interval actually gives you way more information. Beware, oh, I love this. Beware of multiple analyses. So, searching data for patterns is certainly legitimate. Performing every conceivable significance test on data with many variables until you obtain a significant result, that's not okay. All right. That is known as data dredging and p hacking. So, sometimes people will overstep boundaries, I suppose, in stats and say, oh, okay, I'm not getting the results I wanted in this study or this experiment. So I'm going to perform a different type of test, a different sort of inference, and see if now I can get the answers that I'm looking for. And that's not how statistics work. Like sometimes the numbers just aren't there. Maybe your sampling was bad and you need to go revisit that. Maybe it was just a poorly designed study. So you do have to go back to the beginning in many cases and not just say, you know what, I put so much energy into this, I'm just going to make the math work. That is bad stats, as I like to call it. And that's that. All right. So that's the beginning of chapter 11. There's actually only one more section. It's a pretty big one, but I hope you've seen some parallels between the last couple chapters and saw how they all kind of come together to start forming chapter 11. All right. Good luck, everybody.